Okay, so here's our last video of chapter 4 that never ends. So our last topic has to do with what's called stoichiometry, and stoichiometry are the quantitative relations in a chemical reaction. So you can see here stoichiometry means element measure. And so it has to do with quantity. So it's based on the balanced chemical equation. So that's why we already have to know how to balance an equation. And we're going to look at relationships between mass and moles. So because every compound out there has a different mass, we can't compare things directly with mass. And so we're going to go through the idea of a mole because they're all related through moles. So this is, as this says, fundamental to most quantitative work in chemistry. All right, so let's just talk about how the idea of stoichiometry works in everyday life. So let's say we're making a ham and cheese sandwich, and our recipe says we use 2 pieces of bread, 1 slice of cheese, and 3 slices of ham, and that will give us 1 sandwich. So here's our reaction. All right, what if I wanted to make 5.5 sandwiches? Well, you can probably imagine that if you want 5.5 sandwiches, you need twice as many bread, so you need 11 pieces of bread. You'll need 5.5 times 3, so 16.5 pieces of ham, and you'll need 5.5 times 1, so 5.5 cheese sandwiches, and you'll make 11 sandwiches. Obviously, that was a half there. We're assuming everything stays in relationship. So as long as the ratios hold up, everything will be correct. So what if we wanted to make 50 sandwiches, right? 50 sandwiches, we would need 100 pieces of bread. And again, because the sandwich to bread ratio is always 1 to 2, so 50 times 2 is 100. We need 3 pieces of ham for every sandwich, so if we wanted 50 sandwiches, we'd need 150 pieces of ham. And then if we, to make 50 sandwiches, we need 50 pieces of cheese. So get the idea. So the same is true of chemical reactions, as long as we know the ratio. And now here, this was just 1 to 1 to 3. These are actual pieces. But what's going to happen is when we have a balanced chemical equation, we're going to know the mole to mole ratio. So mole to mole, that's what those coefficients mean. So let's look at that a little. All right, so let's say we have nitrogen gas plus 3 hydrogen gas gives me 2 ammonia gas. So we could say 1 nitrogen molecule. So we know the ratio. So we could say, let's put it up there. So we could say 1 molecule of nitrogen reacts with 3 molecules of hydrogen to give us 2 molecules of NH3. That's a perfectly good relationship. But more likely what we're going to do is say 1 mole of N2 plus 3 moles of H2 will give us 2 moles of NH3. What we cannot say, however, is we can't say, well, I couldn't say 1 gram of N2 plus 3 grams of H2 will give us 2 grams of NH3. Obviously, because everything weighs a different amount. Hydrogen's very tiny, nitrogen's large. They all weigh a different amount, so we can't say that. We could, if we wanted to, we could pull in molecular weight, and we could say, since each nitrogen weighs 14, then we've got, if we have 28 grams of nitrogen, and then if each hydrogen weighs 2, 1 times 2 gives me 1 hydrogen, and then there's 3 of them. So if I have 28 grams of nitrogen and 6 grams of hydrogen, they will react to give me, and if each ammonia weighs 17, because it's 12 plus 3, 17. So 2 times 17 gives me 34. So that will hold up. So 28 grams of nitrogen plus 6 grams of hydrogen gives me 34 grams of NH3. But you can see what we had to do here. We had to pull in the molecular weight to figure that out. And so really, our mole to mole ratio, and that's actually what we do when we start with grams. We're going to have to convert to moles by using the molecular weight. So that's where the connection is. We have to convert everything to moles. Okay, so suppose we have this same balanced equation and we want to determine how many moles of NH3 we could produce if we start with 4.8 moles of H2. So we have 4.8 moles. All right, so because of the coefficient, we know the mole to mole ratio. So what we can say here is 3 moles of H2 are equivalent to 2 moles of NH3. That's the mole to mole ratio, or sometimes I think your book also calls it the stoichiometric relationship, or the stoichiometric relationship or ratio. Okay, so in other words, if we have 4.8 moles of H2, how many moles of NH2? We know that for every 3 H2, we make 2 moles of NH3. So here is our conversion factor. We put the one we know on the bottom to try to cancel out, and the one we're looking for on the top. So it'll look like this: 4.8 moles of H2. There are 3 moles of H2 for every 2 moles of NH3. So we would produce 3.2 moles of NH3. And again, that's because of the 3-to-2 ratio. So that's probably the most important thing right here, is to be able to convert from one compound to another. You have to go through the mole to mole ratio, or the stoichiometric ratio, or the stoichiometric relationship. So, but now, obviously, if I went to the lab and I picked and I said I want 3 moles of H2, how would I measure that? I need to know in terms of something that is actually useful. So, and I can weigh. So that's why grams. So here's another example. How many grams of HCl are required to react with 5 grams of manganese 4 oxide according to this equation? So here's our equation. And right now, that's supposed to be an arrow right there. Okay, so right now we have 4 HCl plus MnO2 gives us 2 H2O plus 1 MnCl2 plus Cl2. So this is our balanced chemical equation. Now it doesn't matter which of these you're relating to. So we want to know how many grams of HCl are required to react with 5 grams of manganese oxide. So we're not worried about the other ones. There's going to come a time where we will have to worry, but right now we're just wanting to compare these two. So what do we know? We know that 4 moles of HCl are equivalent to 1 mole of manganese 4 oxide. So we know that that's true. So that's going to be our conversion factor, or our stoichiometric ratio. However, we don't know moles of MnO2 yet. We know grams, so we're going to have to convert from grams to moles, and then we can make this conversion. All right, so there's our balanced equation. First, you know what you're given: 5 grams of MnO2. We have to convert that to moles, because the only way we can convert from one to another is through the mole to mole ratio. So 5 grams of MnO2. We know 1 mole of MnO2 is equivalent to 86.9 grams of MnO2. That's the molar mass, or the molecular weight, from the periodic table. Now we can use our ratio. We want to convert from moles of MnO2, so that's going to go on the bottom to cancel out, and we want to know moles of HCl on the top, so that's our second ratio. 4 moles of HCl for every 1 mole of MnO2. And it doesn't matter what they are, just get it from the balanced chemical equation. Now, finally, the question asked for, it's not up here anymore, but it said, how many grams of HCl do we need? So moles, which is a fine answer, but that's not what they're asking for. They want to know grams. So now we're going to have to convert from moles of HCl to grams of HCl. So now we need the molecular weight of HCl, which is 35.5 plus 1, 36.45, or 36.5 grams per mole. So notice what happens: grams of MnO2 cancel, and then moles of MnO2 cancel, and then moles of HCl cancel, and finally our answer will have units of grams of HCl. So now we're going to take 5 times 1 times 4 times 36.5 divided by 86.9 divided by 1 divided by 1. And what do we get? We get 8.4 grams of HCl. Keep the same number of significant figures that you started with. 5 here. I'm sorry, 3. Looking at the 5 and saying 5. 3 here, 3 here. Okay, so that's the basic process. All right, 3-step process. Write what's given, convert it first to moles. Now here's the thing, what if you're already given moles? Then you don't need step 1 because you already have moles. So, just do the parts that you need. Convert moles of what you know to moles of what you want to know by using the mole-to-mole ratio of the balanced equation, or the stoichiometric ratio, I think your book calls it. And then convert the answer of the new compound into grams if that's what they ask for. So remember that we can only make conversions from one substance to another by using the mole-to-mole ratio from the balanced chemical equation. We cannot compare two things to each other that are different compounds because they all have different molecular weights. So we have to take that molecular weight out of the equation in order to compare them. So that's why moles are part of the whole deal and why we have to use them. Again, only use the coefficient in the second step. Don't use when we made that first conversion and we converted from grams to moles. Whenever you do the grams to moles, it's always 1 mole equals the molecular weight in grams. So you only use the coefficient in that middle step when you're doing the stoichiometric relationship, the 4 moles to 1 mole or whatever it happens to be. So be really careful there. Don't use the coefficient until that middle step. For the conversion of grams to moles, make sure you just always use 1 mole equals the molecular weight in grams, because that's the conversion factor relationship. All right, so here's another example. What mass of water, so I'm looking for grams of water. How many grams, I guess that's what I'm looking for, grams of water. How many grams of water can be produced if I start with 1.5 grams of glucose and it's metabolized in the body by this reaction? So now we've got our relationship of glucose to water. So we know that it's 1 mole of C6H12O6 equals 6 moles of water. But the only way we can convert from glucose to water is by using this mole-to-mole ratio. So we're going to have to start by converting grams to moles. The molecular weight of this, there's 6 carbon, 6 times 12, plus 12 times 1, plus 6 times 16 is 180. Is the molecular weight. Molecular weight of water is 18 grams per mole. So again, remember, it's 18 grams per 1 mole, 180 grams per 1 mole. The 6 only comes into play when we're converting from one to the other. So again, here's our first step. Convert our glucose to moles, grams to moles. I kept 3 sig figs again. Sometimes if you're doing a calculation like this, what I do is put it in my calculator and then I just leave the whole thing. I don't round it in between. I leave the whole thing, then I do my next step, then I do my last step and only round at the end. Because if you round each time, you may end up with some rounding errors. All right, then we take the moles of C6H12O6 and we convert that to moles of water. So we multiply by 6. And then finally, we need to know how many grams it is. So I'm going to convert by multiplying by 18. So it's 0.9 grams of water. 1.5 grams of sucrose will, or I'm sorry, glucose will give me 0.9 grams of water. Again, you don't have to get the answer each time. You could do all 3 steps in a row. Keep your answer in each case. Just like we did on that last problem, or you can do each step and write the answer. Just keep, like I said, keep more sig figs at the end of each problem until the end, and then round. All right, so yeah, just what I just said. Sometimes it's easier to do in one motion, just keeping all your numbers in your calculator as you go. So that's what I did here. So if you just now do also be careful. Notice that if you've got a lot of things in the denominator, you want to hit divided by every time. So I would say 1.5 times 1 divided by 180 times 6 divided by 1 times 18 divided by 1. Now obviously with the ones it doesn't matter, but just be careful that every time you've got something in the bottom you're hitting divided by your calculator. If you tried to say times, you're going to mess yourself up. Okay, round to the correct number of significant figures at the end. Like I said, it's good to keep units. If you keep your units, if you're doing these kind of problems, people get really sloppy. It's kind of easy. You want to be careful, like not just writing grams and moles, but actually what the compound is. Grams of glucose, moles of glucose, moles of glucose, moles of water, so that what's canceling out and what you have. So that's a helpful thing, is to write your units. Just take your time, write your units, and cancel them as they go. And like I said, you don't have to complete all 3 steps if the problem doesn't ask for it. So notice that this first step I was given grams. So if I start with grams, I'm going to have to convert to moles before I can do anything else. So that's this unit. If I'm given grams of A, I have to use the molecular weight of A to convert to moles of A. However, if the question gave me moles of glucose to start with and didn't start with grams, then I would be right here and I wouldn't have to do that first step. So if I start with moles, then I'm starting at this point in the process. Then I have to convert using the mole to mole ratio. So in this case, 6 moles of H2O gives me 1 mole of glucose. And then if the question just says, well, how many moles of water would you produce, then you're done. You've got the answer. But if it says how many grams of water, then you need the molecular weight of the second compound to finally get grams. So all 3 steps if you need to go from grams to grams, but just start with what you're given. If you're given moles and you need grams, then you just do the last 2 steps. If you're given grams and you just need moles, you could just do the first 2 steps. So you don't have to do all 3 if it's not required by the problem. So here's your book does something like this. So if you start with the mass of glucose, you use the molecular weight or the molar mass to convert to moles of glucose. Then you use that stoichiometric factor or mole to mole ratio to convert from moles of glucose to moles of water. And then finally back to mass of water by using the molecular weight of water. This is glucose. Just to point out that this is one really, this is probably the most logical way of doing, or probably the most often used. So we start with grams of something, convert to moles of something by using the molar mass, then use that stoichiometric factor to go from moles of one thing to moles of another. And then if you need grams again, you go back using the molar mass. But we already know how to also use molarity. So remember, molarity is moles over volume in liters. If you rearrange this, you can also have moles as molarity times volume. So that's another way to use this this chart. If you're going from, if you're given a volume of solution A and you know the molarity, then you can use molarity. That would be volume times molarity. That would give you moles of A. Then you can use the stoichiometric factor and you would get moles of B. And then if it happens that B is also a solution and you use the molarity, so moles, if we rearrange this, moles, if we're looking for volume, volume equals moles over molarity. So this time you would want to divide by or multiply by 1 over molarity, and you would get back to volume. So just keep in mind, this is the critical point right here. If you know one compound and you're trying to find the other, you need that stoichiometric factor or that mole to mole ratio. But however you get moles, there's various ways to get moles. So like I said, you can use volume and molarity, or you can use mass and molar mass, molecular weight. What if you were given a solution and molarity and you found moles of A, but then it said find out how many grams of B you can you can make. So you could start with volume and molarity, find moles of B, and then go up to mass of B. So you can follow this any which way. And then just to kind of complete the whole picture here, if it's a pure substance, and they're talking about the volume of a pure substance, so remember this is a solution that has different concentrations. If you know the mass of A but you need the volume of pure substance A, you can also convert it by density. I usually don't pull that in, but if you need to, if you know the volume and you're trying to find the mass and it's a pure substance, then you can convert by density. And same thing over here. There'll be one more part to that when we get to the next chapter, because there's another way that you can find moles. And actually, a lot of times you see charts like this where they talk about the molecules, this Avogadro's number. I don't think that's as useful, and I don't want to confuse the issue. So anyway, different ways that you can convert, but the key is using that mole to mole ratio or stoichiometric factor and that's probably the thing people forget the most, and it's the most important. All right, so one other topic that's related to stoichiometry is limiting reagents. So far, we've only been comparing one compound to one compound, assuming it all gets used up. But we can't always assume that. So the limiting reactant or limiting reagent is the reactant that is entirely... So the limiting reactant, or sometimes it's called limiting reagent, is the reactant that gets entirely consumed when the reaction goes to completion. So you might have more than enough of one of the compounds and just enough of one, and so that one will get used up. So the limiting reagent or reactant is the one that will determine how much you can make. All right, so let's look at again an example from everyday life. Let's say I want to make a bicycle. A bicycle requires 1 frame and 2 wheels. So what if I have 20 wheels and I have 5 frames? All right, let's draw it over here. So I've got a bike. I've got a frame, and I've got wheels. We're just going to worry about frame and wheels. Okay, so I have 20 wheels. So I know that just from what I've been doing, not limiting reactant or anything, if I have 20 wheels, I know because I need 2 wheels for every bike, then I can make 10 bikes. So if I use up all my wheels, I can make 10 bikes. Now let's do the same thing over here. I have 5 frames. I know that I need 1 frame for each bike. So it turns out if I have 5 frames, I can only make 5 bikes. So in this case, frames is my limiting reagent. I can't make 10 bikes because I don't have enough frames to make 10 bikes. Now, so will they be even? No, I can make 5 bikes. And I can use up the wheels that I need to make those 5 bikes, and then I'll have leftover wheels. So frames are my limiting reactant, wheels are my excess reactant, and so the one that gets used up first will limit how much of the product I can make. And so, notice what I did. I actually figured out how many bikes I could make from my wheels, how many bikes I could make from my frames, and then I said, well, I can only make the smaller of the 2, and I'll have leftover wheels. So keep that process in mind, because that's what we're going to be talking about in a minute. So I think, and try to, yeah, like I said, keep the process in mind, because I think, this is common sense, and I think everybody probably understands it. When we start throwing chemistry and numbers in, everybody's like, whoa, what are you talking about? But it's the same process. So again, let me say that one more time. I have 20 wheels. So what I did is I said, how many bikes can I make with those 20 wheels? I can make 10 bikes. How many bikes can I make from my 5 frames? So each reactant, I figure out how many bikes. Which one is the true answer? It's the smaller one, because once I make 5 bikes, I will run out of frames and I'll have extra wheels. So that's sort of the process we do. Figure out how much of one we can make, how much of the product we can make from one thing, how much from the other thing, and then pick the smaller of the two. So here's what I just said. So the frame is your limiting reactant. Here's another example. The limiting reactant analogy using cheese sandwiches. This time we're just going to make real simple sandwiches. A sandwich equals 2 slices of bread and 1 slice of cheese. So very, very, very similar to the bikes. Right here we have 28 slices of bread. So how many sandwiches can I make? Just not worrying about the cheese at all. Well, I know if I need 2 pieces, I can make 14 pieces. I can make 14 sandwiches if I use up all my bread. How many sandwiches can I make from my cheese? Well, I can only make 11 sandwiches because I only have 11 slices of cheese, 1 slice per sandwich. So how many sandwiches I can make? You can actually physically do it. I can make 11 sandwiches. Then I run out of cheese, and then I have, in this case, to make those 11 sandwiches, I need to use 22 pieces of bread. I actually have 28, so I have 6 pieces of bread left. So that's sort of showing you the last step. So I can figure out, I can physically make those 22 sandwiches. I use up 22 slices of bread, so I have 6 slices of bread left over. So it's the same, we're going to do the same thing with chemistry. We just have to do it in more steps because, again, it's the mole-to-mole ratio or stoichiometric factor that's most important here. All right, so let's say this is a reaction we either have already done or will do in lab in this semester. We take zinc and we can react it with hydrochloric acid to give us zinc chloride and hydrogen gas. So we can see here, this is the balanced equation, and so we need 2 hydrochloric acid for every 1 zinc, and we'll get 1 zinc chloride and 1 hydrogen gas. So let's say I have 0.3 moles of zinc, and I add 0.52 moles of hydrochloric acid. How many moles of hydrogen are produced? So a little trick is, or a little hint, or so that you know it's a limiting reactant problem. If you're given both reactants, you need to consider both reactants. So they're telling you, all right, let's see which one runs out or if they're equal. So basically, how much hydrogen can I make? So kind of following the same process that we just talked about, I can say, well, zinc to hydrogen is 1-to-1. So if I have 0.30 moles of zinc, since it's 1-to-1, I can make 1 mole of hydrogen for every 1 mole of zinc. So I can make 0.30 moles of hydrogen. So simple 1-to-1. Well, let's do the same thing with the hydrochloric acid. Well, I start with 0.52 moles of hydrochloric acid. And I say, okay, well, but I need 2 moles of hydrochloric acid. And if I use 2 moles of hydrochloric acid, I only make 1 mole of hydrogen. So I have to divide by 2. So this will only make 0.26 moles of hydrogen. So even though it looks at first like, maybe this was the limiting reactant because it was smaller of the two, but because of the ratio involved, actually the HCl is the limiting reactant because I can, since I need 2 of them for every one, I get 0.26 moles of acid, or H2. So 2 questions. How much H2 can I make? Well, theoretically, I could make 0.26 moles of H2. I can't make 0.3, even though I have enough zinc for it, but I can make 0.26, and then my HCl runs out. Another question I might say is, what is my limiting reactant? HCl is my limiting reactant. I think I work through all this on the next slide. So let's, yeah, so that's what I did. So 1-to-1 ratio of zinc tells me how many moles of H2 I have, and then 0.52 moles of HCl, but 2 moles of HCl for every mole of zinc. And again, you cannot forget this step. Here, I'm not confusing you with other things since I'm starting with moles and asking for moles. We're just doing the one step. Of course, it does get more complicated when we throw grams. If we knew grams, we'd have to convert to moles first and then so forth. But right now we can compare, and we can see that HCl is the limiting reactant, and so the amount of H2 that I can produce is equal to 0.26, the smaller one of the two. So I kind of said this just a minute ago. The theoretical yield then, theoretically, how much can I theoretically make? It's the amount, it's the maximum amount of product that can be made by using up all of the limiting reactant. So when you use the when you figure out what the limiting reactant is, determine how much product you can make from the limiting reactant. That is called the theoretical yield. That's how much I can theoretically make. So in that last example, I could make 0.26 moles of hydrogen gas. That was my theoretical yield. So let's look at another example. This time we got a little more confusing because we have to take grams into consideration. So what is the limiting reactant or reagent when 3.5 grams of copper is added to a solution of 6 grams of silver nitrate according to this reaction? How many grams of silver can be formed? In other words, what is the theoretical yield of silver in grams? Okay, so I just want to point out a couple of things. That question mark should be over here like that. So point out a couple of things. So again, the only way we can convert from one compound to another in a balanced chemical equation is to use the mole-to-mole ratio. And we know that 1 mole of copper is equivalent to 2 moles of silver. 1 to 2. We also know that 2 moles of silver nitrate are equivalent to 2 moles of silver. So that's my mole-to-mole ratio here. Now, it's also true that 1 mole of copper is equivalent to 1 mole of copper nitrate, and 2 moles of silver nitrate is equivalent to 1 mole of silver nitrate, copper nitrate, sorry. And it doesn't matter. I could have picked either product. I decided to go ahead and do the conversion factor using silver because it asks you in the second question. It says, well, how much silver can you make? So you could go through the whole thing and figure out limiting reactant with either product if there's more than one. Doesn't matter. Pick whichever one you want. But do read the question, because in this case, the second part of the question says, well, how much silver can you form? So once if you're already figuring out silver, then you can figure out limiting reactant using silver. Okay, so let's look at the process. Again, I know grams, so I'm going to have to convert to moles of copper. Once I know moles of copper, I can convert it to moles of silver. Here I can take 6 grams of silver nitrate and convert it to moles of silver nitrate. And then using my mole-to-mole ratio, I can convert it to moles of silver. I am going to pause and say something. There are more than one correct way to do this. And so if you've had chemistry before and you've learned it a slightly different way, sometimes some teachers will say, well, let's figure out how much copper you have and let's figure out how much silver you need to react with the copper, and you kind of compare and see which one do you have more of. And that's a perfectly fine way of doing problems as well. In my opinion, it seems like it's a little bit more confusing, but if you do it correctly and you do it a slightly different way, as long as you're showing me how you're doing it, I don't care. So this is my way. I always think it just makes more sense for me to say, well, how much silver can I make from the copper? How much silver can I make from the silver nitrate? And then just see which is smaller. Again, just two different approaches. So there's more than one way, and it doesn't help me to give you the different ways because that'll just confuse you. But if you already learned a different way, by all means, go ahead and do it that way. So I already told you this hint. Make sure and see which one you're talking about, and it'll save you some time. All right, so anyway, start with what we know was 3.5 grams of copper. So 3.5 grams of copper, the molecular weight of copper, or the molar mass of copper, is, where's my pen, 63.5 grams of copper per mole. So first I'll convert from grams to moles of copper. Then I know I've got 1 mole of copper for every 2 moles of silver. So the copper cancels out. Now I know how many moles of silver I need. And then I can actually convert that to grams because it wants to know how many grams of silver I can produce. So 11.9 grams of silver can be produced from 3.5 grams of copper if all the copper got used up. We'll do the same thing now with the silver nitrate. We're given 6 grams of silver nitrate. We have to convert that from grams to moles. Silver weighs a lot, as you can see. So grams of silver nitrate converting to moles of silver nitrate. And you can stop and get the answer to each step if you want to, or you can just do the whole process. Now I can convert from moles of silver nitrate to moles of silver. It's a 2-to-2 ratio or a 1-to-1 ratio, either way. 1-to-1, 2-to-2. And then finally at the end, I can convert from moles of silver to grams of silver. And I see that I can only, in this case, I can only make 3.81 grams of silver. So that's my theoretical yield. And my limiting reactant, so this is not my limiting reactant because this is my product. My limiting reactant is the silver nitrate. That's the one that got used up before the other one. So I could actually, if I brought more silver nitrate to the table, more than 6 grams, I could actually make more silver because I could make up to 11.9 grams if I used up all the copper. But the silver nitrate runs out first, and so this is the most I can make. So again, terminology, silver nitrate is the limiting reactant. It gets used up first because we only have enough to make 3.81 grams of silver, even though there's more than enough copper. So limiting reagent, and that means my theoretical yield is 3.81 grams of silver. So this does take some practice as well. There are some practice review sheet online having to do with limiting reagents and theoretical yields. I've got one more example here for you. So let's, if I have 4.1 grams of chromium and I react it with 9.3 grams of chlorine, how much chromium chloride can I produce? So here's the balanced chemical equation. You want to make sure it's balanced beforehand. So 2 chromium, 2 times 3, 6, 3 times 2 is 6. So again, I start with my chromium, 4.1 grams, convert that to moles. Convert moles of chromium to moles of chromium chloride, and that's a 1-to-1 ratio or 2-to-2 ratio. And then convert to molecular weight of chromium, and so I could make 12.5 grams of chromium chloride. Do the same thing with the chlorine, 9.3 grams of chlorine. I have to convert to moles of chlorine. 1 mole is equal to 70.9 grams. And then notice 3 chlorine to 2 chromium chloride. So now I've got to multiply by 2, divide by 3, then multiply by the molecular weight of chromium chloride, and find that. So which is my limiting reactant? Chromium is my limiting reactant because it gets it once I get to 12.45 grams of product, the chromium gets all used up. And what's my theoretical yield? 12.5 grams is my theoretical yield. Okay, I will say some people actually, if you notice this last step, you're actually doing that twice. So if you wanted to, if you after the second step, you could compare and decide which is the limiting reactant, and then you only have to do this multiplication for one answer. So at this point, if you had done it, you would find out that you had, where'd my pen go? There you had 0.0788 moles of chromium chloride and 0.0874 moles of chromium chloride. So still already this would be your limiting reactant. And then you would only have to do multiply that by the grams to get 12.5 grams. You wouldn't have to do this last step. But either way, it doesn't matter as long as you compare the two. But it's really important that you do the mole-to-mole ratio before you compare the product to see which one's smaller. This is absolutely important, and so many people forget it. So don't forget, the mole-to-mole ratio is the most important step. So we could ask one more question. How much Cl2 will be left over? We know that Cr gets used up. It's the limiting reactant. So how much will be left over? Remember how I did that with the bikes? Let's just remember for the bikes, we had 20 wheels and we had 5 frames. So I knew I could make 5 bikes from the frames and I could make 10 bikes from the wheel. So there's a couple of different ways that I could do it. I could subtract the bike, so I know I can only make 5 bikes, and so I have enough wheels to make 5 bikes left. So then I would multiply by 2, and I know I have 10 wheels left over. Or the other thing I could do is I could say, well, if I make 5 bikes, yeah, sort of the same thing. If I make 5 bikes, I need to use 2 wheels for each bike, so I have 10 wheels. And if I started with 20, then I have 10 left over. It's unfortunate I used 10. I should have used a different number, but see if you get the idea. There's a difference. Is either figure out how many wheels you need to make the 5 bikes, and then subtract them from how many wheels you had. That's probably the easiest way. So in this case, how much Cl2 will be left over? Well, since we can produce 13.8 grams of the CrCl3, and we can only with the chlorine, but only 12.5 grams from the chromium, that means I can make 1.3 grams more CrCl3 from the Cl axis. So if I convert 1.3 grams of CrCl3 back to chromium, so 1.3 grams of Cl3, and now I've got to go all the way back through all my steps. So I use the molecular weight of CrCl3 to get the moles of CrCl3. Then I'm converting back to how much chlorine that will need to be, how much chlorine will make this amount of chromium chloride. So back undoing my mole-to-mole ratio, and then the molecular weight of chlorine. So I'm kind of just undoing everything. But the first thing I did was subtract to see how much more of my product I could make from the non-limiting reactant. And so that's 0.87 grams of Cl2 left over. Or the other method, like I said, is I could just say, all right, here's my limiting reactant, 12.5 grams. That's all I can make of the CrCl2. How much chlorine do I need to make 12.5? And then subtract that from what I started with. So here I just take my smaller amount. I say, okay, if this is the most CrCl3 I can make is 12.5, how much of the chlorine gets used up to make that? So sort of similar to my 5 bikes. I needed 2 wheels to make my 5 bikes, so I had 10 wheels, and I started with 20, so I have 10 left over. So same idea. If I want to make 12.5 grams of chromium chloride, again, I have to undo my mole to gram to mole ratio and then mole to mole ratio. So this tells me that in order to make 12.5 grams of chromium chloride, I need to use 8.4 grams of chromium chloride. Well, I started with 9.3 grams, so 9.3 minus 8.4 is 0.90 grams. These are a little bit rounding errors, so these are pretty much the same number, maybe just not rounded quite. If I had used probably more 3 significant figures here, I might have come in closer. But anyway, that's the process. Either figure out how much of the product what's your theoretical yield, how much of the excess reactant do you need to make that much product, and then subtract from the original amount, or subtract at the end. But just realize that when you subtract at the end, the 1.3, that's not how much more chlorine is left over. That's how much more CrCl3 I could make if I used up all the chlorine. So 12.5 is what I can make if I use up all the chromium. 13.8 is what I can make if I use up all the chlorine. So 1.3 is how much more chromium chloride I can make if I used up all the chlorine. So that's what the subtraction. So you still have to convert it all the way back to chlorine in order to get the answer. Okay, one other idea is called percent yield. So you've been in the lab probably enough to realize that reactions are not theoretical. Sometimes the reaction doesn't go the way you expect it, so it's not complete. There's weighing errors, of course. Sometimes if you're trying to collect a product, you're not going to be able to get every drop. Some will be left over in the beaker. You might spill some, etc. So anyway, what chemists often will report is called the percent yield or percentage yield. Percent yield is just the actual yield divided by the theoretical yield times 100% to get percent yield. So, theoretical yield, we know how to calculate that using the limiting reactants to find the theoretical yield. The actual yield is what if you actually ran the lab and you collected the stuff and you actually measured it, that's how much the actual yield is. So in that, let's say we figured out that we could theoretically make 12.5 grams of CrCl3. What if we actually only produced 10.6 grams? What's the percent yield? Well, 10.6 is actual divided by 12.5 theoretical times 100% is 84.8%. So we were able to produce 84.8% of what we thought we could. And that's actually a pretty good considering working in the lab. That's not a bad percentage. So kind of carrying on with the same theme, the study in chemistry, the study of quantitative analysis, you can see right there in the name, is figuring out how much of something you have. So it's a kind of a branch of chemistry. Let's say you worked in a factory and the solution that was used to wash something had to be a certain concentration, and it had to be monitored because it could change often. So there was somebody who has to go take that solution and test it to see what the concentration is over and over again so that it stays correct. Well, that person would be doing quantitative analysis on the solution to make sure that it's the correct amount, to see what the concentration is. So the area of chemistry is called analytical chemistry, and that has to do with figuring out how much of something you have. Now, this is really in opposition to qualitative analysis, would just be identifying what it is, whereas quantitative is telling you how much you have. So it's the determination of the amount of a substance or species present in a material. There's two major types of quantitative analysis that we can look at. And one is called volumetric analysis, which is like a titration. And at some point in this semester, we will do one of those. And then the other one is gravimetric analysis, which is based on weight. So let's look at titrations. This is an important method for determining amount of a particular substance. So like I said earlier, if you're trying to measure the concentration of a solution, you probably would do volumetric analysis, which is a titration. So it's a way of determining how much of one substance you have by adding a carefully measured amount of another substance that we know will react with the first substance. So what we do is we add just enough of substance B, and we know the exact concentration of substance B. So if we know the concentration and how much of it we added, we'll know exactly, and if we know the ratio of A to B, then we can find out how much of A we had. The equivalence point, or sometimes also called the end point, is the point in the titration where the stoichiometric amounts are equal, so A and B. Often some titrations are very simple and it's a 1-to-1 ratio. So at that point, it's how that the amount of A equals the amount of B, although the ratio might be different, so you have to be careful. But anyway, we see the end point. Oftentimes we put an indicator in our solution to change that changes color at that point, and so we know where to stop, and then we can do the calculations. So volumetric analysis is based on titration, like I said. So let's look at this reaction, and here's why it's important to note those stoichiometric amounts. So it's not always 1-to-1. So in this case, I'm using sulfuric acid and sodium hydroxide, so it's a 2-to-1 ratio. So suppose we have a beaker, and it has 35 milliliters of 0.175 molar H2SO4. And we want to know how much of the 0.250 molar NaOH must be added to completely react. So there's a couple of ways we could do it. We could actually start with, well, in this case, we want to know how much of this we're adding. So this will be in the beaker concentration and amount, and then we're adding another amount to it, and they have to, the moles have to be equal. So what we need to know is we know how many moles, we need to find out how many moles of H2SO4 we have. So we're using molarity, since the molarity of the H2SO4 is given to you as 0.175 moles per liter. So we have to convert milliliters to liters. So 0.035 liters. If we cancel liters out, then this answer will give us moles. But we're not done yet because we want to relate it to NaOH. So now we have to use the stoichiometric factor from the Pound's chemical equation. So we know that we need 2 moles of NaOH for every 1 mole of H2SO4. And then finally, so if that converts, that cancels out moles. So now we know how many moles of NaOH, but we want to know how many milliliters that's going to be. So we need, again, to use the molarity of the NaOH. And so this time we know moles are on the bottom, liters are on the top. So when we calculate this out, we'll get how many liters of NaOH. We need to add 0.0490 liters, which is the same as if you move it over 3 places. 49 milliliters of NaOH. So here's where I was saying it's again, it's always important. Now, a lot of titrations are 1-to-1, so it's not critical to do this step, but it is important to recognize if it's needed. So we're converting from using molarity to convert to moles, then we're using the mole to mole ratio, so this is stoichiometry again, and then we're using the molarity to convert back to milliliters. So that's volumetric, and we would stop the titration when the color changed. This is what's a burette is what's often used for a titration. You can see the student is filling up a burette here. They allow measuring to 0.01 milliliters. So each of this is a 0.1, and then in between, so I can't draw. So this is obviously 0, 1, 2, and then this is 1.1, 1.2, 1.3, 1.4, 1.5, so forth. So you can actually estimate in here, so you can estimate to 2 decimal places. So if I was like right in between here, I'd be at 1.45. I can estimate. Gravimetric analysis is the other type of quantitative analysis. This time, gravimetric is based on weight. So what happens is we can convert the species in question to a product that, like a precipitate, that can be isolated and weighed. So let's look at an example of that. Like I said, the precipitate is filtered dried. Actually, you have to filter it, dry it, and weigh it. We're not actually going to do one of these this time, but hopefully you can imagine we do the precipitate lab where we're making a solid. We didn't actually collect it, but you can collect it and weigh it, and then you know how much you have. All right, so let's look at this problem to determine how much lead is in a sample of drinking water. So if I have a flask of drinking water, and I add sodium sulfate to the water, the sodium sulfate will precipitate any lead that happens to be in here. So lead sulfate, PbSO4, is the product that will precipitate, and I'll filter it and I'll collect it and then dry it. So here's the reaction, Na2SO4. If there's any lead in the drinking water, it'll be hanging around, and then it'll precipitate with the sulfate to make lead sulfate, and it's a precipitate, so it's not going to be hanging around in the water anymore. So it's a precipitate. Like I said, we can filter it, and we can then dry it in an oven, make sure there's no water left in it, and then weigh it. So let's suppose that we have 1 liter of our solution. I'll go ahead and draw that here. So we have 1 liter of water. And we add enough sodium sulfate so that we precipitate all the lead that's in 1 liter. And then we collect the lead sulfate, not the lead, but the lead sulfate. We collect it and we weigh the precipitate, and it was 229.8 milligrams. And the question is then, what is the mass of actual lead? So remember, lead sulfate has sulfate now, so it weighs more than the actual lead. So what's the mass of the lead in the water? And they're telling you to express the answer as milligrams of lead per liter. Well, that's not hard because we have 1 liter. So whatever the milligrams is, that'll be per 1 liter. Okay, so here's our balanced equation, and note that, well, these are 1 to 1. So 1 Pb2 plus gives me 1 PbSO4. So 1 lead ion will give me 1 lead sulfate. So that's good. It's 1 to 1 ratio. So now we know the mass of PbSO4, and we can find out how many moles of PbSO4 it is, because we're going to have to, because again, everything weighs something different. So the only way we can convert from one to another is using the moles. So once we know how many moles of lead sulfate we have, we can use the stoichiometric factor to figure out how many moles of lead we have. And we know it's 1 to 1, so that's not hard. And then finally, we can convert moles of lead to grams of lead. So the amount of lead in the sample was 229.8 milligrams. Now here's something you're probably this might stress out some people. So I could do this problem one of 2 ways. We know that the molecular weight of lead sulfate is 303.27 grams equals 1 mole. But notice that I have this in milligrams. So one thing I could do is I could convert this to grams. So I could start out by saying 2298 grams. And then I could say 1 mole of PbSO4 equals 303.27 grams. And then I use my 1 mole of lead equals 1 mole of lead sulfate. And then I know that 1 mole of lead equals 2. And if I did that, I would get this answer, 0.170 grams. But I think the question asks you for milligrams. So then that's easy. I could convert that back, 157.0 milligrams. It's kind of like an extra little step because you had to take milligrams and convert to grams and then go through all the steps and then take grams and convert back to milligrams. So what I did here, and if this upsets you, don't just go, you just do it the other way that I just showed you. But if it's grams equal moles, if you take milli of both sides, it's like dividing both sides by 1,000. So you could also say 303.27 milligrams equals 1 millimole. So that's what I used. I just said 229.8 milligrams, 303.27 milligrams per millimole. 1 millimole of lead sulfate equals 1 millimole of lead, and then lead ion is 207.2 milligrams per millimole, so then my answer was in milligrams. Either way, works the same way. If you convert to grams and go through it, then you have to convert back to milligrams. So anyway, I would just say the amount of lead in the water is 157 milligrams per liter. So that is a very, very long chapter. What should you be able to do when you are confident in chapter 4? You should be able to write and balance a chemical equation. You should be able to define and classify reactions into the 3 common types: precipitation, acid-base, and oxidation reduction. You should be able to use solubility rules to determine if a compound is soluble, if a salt is soluble. You should be able to write any soluble compound in terms of its dissociated ions. And then predict if a solid will form in a precipitation reaction by using the solubility rules. So that would be like if you're given 2 reactants, swap partners, figure out what your possible products will be, and then use solubility rules to determine if one's a precipitate. And then be able to write the molecular, complete ionic, and net ionic equations for these reactions. Be able to classify an acid or a base as weak or strong. That's mostly just by looking at that chart. Be able to write molecular, complete, and net ionic equations for neutralization reactions. So remember, if you have a strong acid or a strong base, they completely dissociate, so you do write them as their ions. But if an acid is weak or the base is weak, we keep it stuck together for the ionic equation. You should be able to assign oxidation numbers to elements in a compound or even an element in an element. You should be able to balance a simple oxidation reduction reaction, and that does not include the one in your book. The only one that I had in this PowerPoint, which would be to put in the electrons and then make sure the electrons are balanced before you add the half reactions back up. So your book is a little more complicated than that, so you don't need to do that for the test. Be able to calculate molarity for moles and mass and volume. So if you're given mass, you'll have to convert to moles. Remember, molarity is moles per liter. So if you know volume, molarity, and moles, you can find if you know 2 out of the 3, you can find the third. And then if you know moles, you can convert between mass and moles first. So if you know mass, you can find moles and then find molarity. If you know molarity and liters, you can find moles and then convert to mass. So that's how they're related. Be able to explain the concept of stoichiometry as it pertains to chemical reactions. Use balanced chemical equations to derive stoichiometric factors relating amounts of reactants and products. So basically it's saying find the mole to mole ratio if you have a balanced equation. Perform stoichiometric calculations involving mass and moles or solution molarity. So, basically, if you know the mass, convert to moles, and then use the mole to mole ratio to convert to the second compound, and then back to grams. Or if you know molarity and volume, you can also find moles and then do stoichiometric calculations using the mole to mole ratio. Be able to explain the concepts of theoretical yield and limiting reactants. Be able to find the theoretical yield for a reaction. If you know the reactants, the amount of reactants. Be able to calculate percent yield if you know the actual yield. And describe the fundamental aspects of titrations and gravimetric analysis, just the very basics. What do you use? And then be able to perform stoichiometric calculations using typical titration and gravimetric data. So again, a huge amount on this chapter. That's why we take a long time to go over it. Thanks for listening.